Right. Good afternoon to everyone. Today we are in the third day, and the third day we will be starting the shallow foundations. Today we will be doing some calculations also. Therefore, please make sure that you will have some books or some papers to write down and a calculator with you. This is the book that I refer for this set of notes. I mean, I have extracted some theories or some pages from this book, The Fundamentals of Geotechnical Engineering, written by Braja M. Das. And first we will see what these shallow foundations are. Shallow foundations, you can draw them. The shallow foundations or the bearing capacity and the settlement. That is what these are the things that we are going to learn in this subject in this under this topic. The lowest part of a structure is generally referred to as the foundation. The foundation means the lowest part of the structure. Its function is to the function of the foundation. The function of a foundation is to transfer the load of the structure to the soil. Now you have the superstructure on top of the soil. Then the function of the foundation is to transfer the load from the superstructure to the soil on which it is resting. That means soil. A properly designed foundation is one that transfers the load throughout the soil without overstressing the soil. A properly designed foundation is one that transfers the load throughout the soil. When you have a structure, let's take a home or whatever like this on the soil, the load will be transferred to the ground through the foundation. Overstressing the soil can result in either excessive settlement or shear failure of the soil. Therefore, when we design it, we should be well aware of removing or we should be well aware of the settlements of the soil and the shear failure of the soil, both of which cause damage to the structure. If there is any settlement in the soil, then the structure will settle, or there may be some cracks. If there are some shear failures of the soil, again the structure will fail. Therefore, geotechnical and structural engineers who design the foundations must evaluate the bearing capacity of the soils. Now, the basic idea of this topic is to check the bearing capacity of the soil and design the shallow foundations. Depending on the structure and soil encountered, various types of foundations are used. There are different types of foundations. First one is spread footing. spread footing is simply an enlargement of a load-bearing wall or column that makes it possible to spread the load of the structure over a larger area of the soil. That is a spread footing. In soil with low load-bearing capacity, the size of the spread footings is required impracticably large. When you have a low load-bearing capacity of the soil, then the size of the spread footing is high, or that is large, and that cannot be practical. In that case, it is more economical to construct the entire structure over a concrete pad. This is called as mat foundation. We will see the photographs later, and we have the mat foundation there. The mat foundation, there is a series of the structure is over a concrete pad. Then we have the pile and drill shaft foundations. Pile and drill shaft foundations are used for heavier structures when great depth is required for the supporting the load. That means the shallow depths are not enough the shallow depths cannot bear the required load. Piles are structural members made of timber, concrete, or steel that transmit the load of the superstructure to the lower layers of the soil. The piles, what do? Is they transfer the load from the superstructure to the lower layers of the soil. According to how they transmit their load into the subsoil, piles can be divided into two categories. We will learn them later, not in this subject. They are friction piles and end-bearing piles. In the case of friction piles, the superstructure load is resisted by the shear stresses generated along the surface of the pile. Now, sometimes you might have heard this. In the friction piles, what happens is you have the pile, and the friction in the surfaces of the pile can resist the load. Let me see what it is. I don't know why. I mean, there's a request. Shall we see? Even though I admit the previous week also that happened. I admit him, but he's not. His name is not showing. But if you log, please log using the registered email address. Then only no one has to admit it. Right. In the end-bearing pile, the load carried by the pile is transferred or transmitted at the tip. That means the bottom part of the pile to a firm strata. We will see them in the deep foundation. In the case of drill shaft, a shaft is drilled into the subsoil and then filled with concrete. A metal casing may be used while shaft is being drilled. The casing may be left in a place or withdrawn during a placing of concrete. Generally, the diameter of a drill shaft is much larger than that of a pile. The distinction between piles and drill shafts become hazy at an approximate diameter of 1 meter, and then the definitions of nomenclature and inaccurate. Right? They are the drill shafts. We will not be discussing about the drill shaft in this subject. And then spread footings and mat foundations are generally referred to as the shallow foundations. Now, and the pile and drill shafts are classified as deep foundations. What we discuss in this topic is the spread footings and the mat foundations. Basically, the spread footings are what we are discussing today under our topic. In more general sense, shallow foundations are those foundations that have a depth of embedment to width ratio approximately less than 4. The shallow foundations, if we define a shallow foundation, those foundations that have a depth of embedment, the embedded depth to the width ratio approximately less than 4. That means the depth of embedment. Now, if I draw a foundation, if this is the foundation, if this is the ground surface, this is the depth of foundation or the depth of embedment. Right? Depth of embedment and width. It means this one. Shall we take the width as B and depth as D? Then what does it say? This that have depth of embedment to D divided by B less than 4. That means D should be, the depth should be less than 4 times of the width. Again. This depth should be less than 4 times of the width of the foundation. That is the definition of shallow foundations. Right. If you have anything to note down, please note it down. Right. Then if that ratio is greater than 4, then it may be classified as deep foundation. In this chapter, we discuss the soil bearing capacity. Let me take the highlighter. Right. In this chapter, we discuss the soil bearing capacity for shallow foundations. As mentioned before, for a foundation to function properly, the settlement of the soil caused by the load must be within the tolerable limit, and the shear failure of the supporting soil, the shear failure must not occur. Therefore, the settlement part would be considered in another section, another topic. But now we will be discussing the shear failure part. Right? For that, first we will see what is this ultimate bearing capacity. Basically the maximum, or what is the ultimate bearing capacity of shallow foundations. Consider a strip. Theoretically, length is infinite. Right? Length is infinite, that is theoretically, but practically that is not. That foundation resting on surface of a dense sand or stiff cohesive soil, as shown in figure 12.1a. 12.1a, yes, 12.1a, 12.3, 12.1a, that is this one. That means this is the foundation, just like random rubble masonry, right? This is the foundation. And here 12.1b, this is the foundation. Just like Kalugalbemi, that is what is that? Random rubble masonry, RRM. As you can see here, the failure surface of the soil might be this way, or this way, or this way, this way. These can be the failure surfaces, right? This way or this way, this way. We will see. As shown in figure 12.1a, with a width of B. Now, if the load is gradually applied to the foundation, the settlement will increase. The variation of the load per unit area on the foundation Q with the foundation settlement is also shown in figure 12.1a. At a certain point, when the load per unit area equals Q ultimate, there's a particular point where the load per unit area equals QU, that is the ultimate bearing capacity. There will be a sudden failure in the soil. Supporting the foundation will take place. There will be a certain failure that will take place, and the failure surface in the soil will extend to the ground surface. This load per unit area QU is usually referred to as the ultimate bearing capacity of the foundation. This is called as the ultimate bearing capacity of the foundation. When this type of sudden failure in soil takes place, it is called as the general shear failure. Now, in exam, sometimes you might be asked, please briefly explain what is general shear failure. Now, you will have to explain like this. Right? Now, if the foundation under consideration rests on sand or clay soil of medium compaction, an increase of load on the foundation will be accompanied by an increase of the settlement. Right? If it is sand or clay soil, then it will be accompanied by increment of the settlement. However, in this case, failure surfaces in the soil will gradually extend outward from the foundation as shown by the solid lines in the next figure. And when the load per unit area of the foundation equals Q ultimate, the foundation movement will be accompanied by sudden jerks. A considerable movement of the foundation is then required for failure surface in soil to extend the ground surface. Right? These are called the first failure load and the local shear failure, blah blah. Likewise, then punch-in shear. We have so many shear failures regarding the strip foundation. As you can now you can see those figures, but based on the experimental results, Vesic proposed a relationship for the mode of bearing capacity failure foundation rest on sands. And the Vesic's test results for the modes of foundation failure for this type of foundations based on the dF over B value and the relative density and B value and B times L value. No, what this dF is the depth to the foundation. dF is the depth to the foundation. Now, and B is the width of the foundation. L is the length, and dF is the depth to the bottom of the foundation from the ground surface. Based on them, you can find the modes of found results, modes of failure. If it is a general shear, then this part will be having the point which represent the DFOB and DR will be somewhere here. DR is the relative density of sand, depth of foundation, width of foundation, length of foundation. So you can plot the points for a particular scenario, and then you can see which kind of which mode of failure would occur. And for the foundations at a shallow depth, the ultimate load may occur at a foundation settlement of 4% to 10% of B. The condition occurs with the general shear failure in soil. However, with local or punching shear failure, the ultimate load may occur in settlements of 50%, 15% to 25%. Okay, and this is how you can find the effective width in case of calculation is dF over B star. Okay, now what we want to discuss in this subject is to basically this one, ultimate bearing capacity. Right? This is the most important thing in this topic. And Terzaghi is the man. Terzaghi in 1943 was the first to present a comprehensive theory for evaluating the ultimate bearing capacity of rough shallow foundations. According to his theory, the foundation is shallow if the depth dF of the foundation is less than or equal to the width of the foundation. Now, as per Terzaghi, that D over B ratio, this one, this is not there. This 4 is not there, right? Depth of the foundation and the width of the foundation is also only there. And later they have found it as 4 or 3. Later investigators, however, have suggested that foundations with DF equal to 3 or 4 times of the width of the foundation may be defined as shallow foundations, right? Right. And this shows, now this is the DF, depth of foundation, and the width of the foundation. Now we will see what this figure is. Terzaghi suggested that for a continuous or strip foundation, the failure surface in soil at ultimate load may be assumed to be similar to that in figure 12.3. It is something like this. The failure mode or the failure surfaces would be something like this. And the effect of soil above the bottom of the foundation may also be assumed to be replaced by an equivalent surcharge, gamma dF, and the failure zone under the foundation can be separated into 3 parts. The failure zone under this can be separated into 3 parts, and the applied load is Q equals gamma dF. Right? First one, triangular zone ACD, immediately under the foundation. Triangular zone ACD, immediately after the that is ACD, this one, right? That is the triangular zone immediately after the foundation, under the foundation. And then the radial shear zones, ADF and CDE. ADF and CDE, these radial shear zones, with curve CE being arcs of a logarithmus, right? Shall we draw that one in this color? AC, AD, sun. Right. And the radial shear zones. Then two triangular Rankine passive zones, AFH and CEG. AFH and CEG. That is the third one. This triangular area and this triangular area, right? The angles CAD and ACD are assumed to be equal, and that is friction angle. That is alpha is friction angle, and we can delete that. Right. And those 3 parts are here. This is cohesion part, this is the surcharge part, and this is the shape from the shape. And this is the equation for the ultimate bearing capacity of the soil. Using this equation, we can find the ultimate bearing capacity as per Tersagi for a strip foundation. For a strip foundation. Now we will see what these terms are. Right? Now the main terms C dash. C dash is the cohesion of the soil. Gamma. Gamma is the unit weight of soil. And Q equals gamma dF. Yes, this Q equals gamma dF. And these three factors, NC, NQ, and gamma, are the bearing capacity factors that are non-dimensional. That means no dimensions or units are there, no units, and are only functions of the soil friction angle. So you can find no for a, now this is the equation for a strip foundation, and this is the equation for a square footing. Now normally we are designing, or we are constructing square footings for the houses, and this is that. And for a circular footing, the equation is this one, right? And now we will see how we can find NC, NQ, and gamma. Before that, if you have to note down anything, you can note down. I think you will need these equations, or else I can. Yes, you can write it down. Then I will upload that PDF now, so that you can get it. Let me share the PDF with you. How may I classwork? Create no. Create material title. Day 3. Shallow foundations. Then I will drag and drop it here. Why is it draft? Edit material. Upload. Yep, it is being attached now. Umasha Sandagi. I think they used to log in from their own some other link, some other email. Right. Now you can see you can get the PDF version of this presentation. Visitors are in this meeting. Open the people to see. I think Umasha, you might have logged in using your own email address. Sometimes that is why I have to admit you. Next time, log in using your registered email address. I think that should be the Lincoln email address. Then automatically you will be entered into the classroom. Otherwise, if I am sharing the presentation, then I will have to come back, and if I did not hear you that tong sound, then you will be waiting. Right. This is how you can find the NC, NQ, and gamma values. They are given in tables based on the 5 values. That is the friction angle values, right? Based on friction angle values, you can find the NC, NQ, and gamma values. As an example, if we take phi equals 30 degrees, if the friction angle is 30 degrees, then the NC value would be 37.16. NQ and gamma values are given here. That is very easy. Or else you can use the equations. There are equations for the NQ, NC, and N gamma. First, we can find the value for NQ using this equation, tan squared 4 phi blah blah blah, and then you can find the NC value using this equation, and then N gamma value. Right? And then we have another method, that is the first one is the oh, very sorry. I think I did not share. මෙතන මේගොල්ලෝ බලන් හිටියට කියන්නේ I forgot to share the screen. Now these are the tables which describes you can find the NC, NQ, N gamma values from these values, and as an example, if I took the friction angle as 30, then NC value is 37, NQ, N gamma. Right? You can find the values. Or else you can use these equations. You can use these equations to determine NC, NQ, and gamma values. If if the phi dash value is given, then you can determine this NC, NQ, and gamma values. Okay, if you need anything to note down, You can note them down. Right. That is the Terzaghi's method, and this equation is by the Meyerhof, and you have a different set of numbers or some large number of parameters to determine the ultimate bearing capacity. But first, we will do some example on that Terzaghi's method. Right. This would be the example. A square foundation that is 1.5 meters in plan. The soil support in the foundation has a friction angle of phi dash and C dash given. The unit weight of soil gamma is given. Determine the allowable gross load on the foundation with the factor of safety 4. Right. Assuming that the foundation depth of the foundation is 1 meter, and use equation 12.4. What is that? 12.4. 12.4 means this equation, that is for a square footing, right? We will discuss this example before going to the Meyerhof method. Right. Okay. Please draw a picture. It shows this thing. Start with me. That foundation is 1.5 meters in plan. Now this kind of footing. This will be 1.5 times 1.5. That means this length would be 1.5, and the soil supporting depth of foundation. This depth of foundation, this is 1 meters, and right, the properties are given: phi dash value, C dash, and gamma. Right. Then you can find NC, NQ, N gamma, because you have to use them in the equation. Right. First find NC, NQ, N gamma, then apply that equation. That's very easy. Quickly do it and tell me. If you have any questions, please ask me. If you have any questions, please ask. Yes, what did you find this in C and Q and gamma? අනේ ඔයගොල්ලෝ කරන්නේ ඉතින් 5 dash is 20. Just tell me the NC, NQ, and gamma values. So tell me the values for this NC, NQ, and gamma by looking at this table. This if you do not respond, I will not continue, right? I mean, you will not be able to do it in the exam. Are you there? Sasi, Buddhika, Umasa.
So,
Yes.
NC value is 14.83.
Okay, we will see. NC value is 14.83.
83.
Okay. Uh-huh.
And NQ value 6.4.
Okay, let's see. Then N gamma. I have shared that PDF in your classroom, right? N gamma.
Okay.
You have to you can just check this table. N gamma is 5.39. I mean, if you are not working with me, don't think that I mean you will be able to do it alone. If you think that you can study these things alone, then no need to come to the class, right? Then how would you find the ultimate bearing capacity using this equation 12.4? Using, you can use this equation. When you use this equation, now NC value is okay, NQ value given we have found it, and gamma value is also found. What is this C dash, Q, B, and gamma? C dash, I think C dash is given in the question. C dash is given, right? And what is that? Q. Q is the effective stress at this point. Q is the effective stress at this point. Effective stress is the total stress minus pore water pressure. Total stress minus pore water pressure. මම දන්නවා මෙහෙම කිව්වට ඔයගොල්ලෝ දන්නේ නැහැ කියලා ඒවා. I will explain it. And B is 1.5. B is 1.5, and the other one is gamma. Gamma is 17.8. Right? Okay, now shall we start this one? There's that equation. Right. Using the equation 12.4, then QU equals 1.3. Yeah, increase the font size so that it will be clear to you. You should be this 1.3 multiplied by C dash. C dash is 15.2 multiplied by NC. NC value, we will see that from the table 20 phi equals friction angle 20. The 20 you might have referred this table. That is wrong, right? This is for the equations 12.6, 12.7, and 12.8. However, whoever the student who has replied me, thank you for your reply, but you have used this table, not this one. You will have to use this one for the equations 12.3 and 12.4. Therefore, the phi dash equals 20, then we will have these values 17.69.
Okay, sir.
දැන් එහෙම කිව්වම තමයි මේ මොකද්ද අපිට වැරදි තේරෙන්නේ. දැන් ඔයා කවදාවත් මේ අරක ඒකට බලනකොට තේරෙනවනේ මේ හරියට බලන්න ඕනේ කියලා. අත් එහෙම කතා කරපු එක හොඳයි. ඒක ඔයා කිව්ව එක හොඳයි. නැත්නම් ඒකට පැටලෙන්නේ නැහැ දැන්. ඒ වැරදුනානේ. වැරදුනහම then ඊළඟ පාර ඔක වරදින්නේ නැහැ. NQ is 7.44. 7.44 in gamma. Gamma. Sometimes there might be a symbol. Yes. NC, NQ, N gamma. N gamma is 3.64. 3.64. Right. QU. I will put this NC 17.69. Right. The first part is okay. This part is written. Plus QNQ. Q is the effective stress at the bottom of the foundation. And you can find the effective stress equals total stress minus pore water pressure. Total stress minus pore water pressure. How would you find the total stress? Total stress can be found by gamma H minus gamma soil, right? This is gamma water times H. මේ අපේ සබ්ජෙක්ට් එක ගන්න මේ බේසික් කතන්දර. Gamma soil times H multiplied minus. This is how you can find the total stress, effective stress. This H is the total height and this H is the water height. Since you don't have any water here, then effective stress is equal to the total stress. Since you don't have water here, then effective stress is simply equal to the total stress. Right. Q is gamma soil. Gamma soil is 17.8. 17.8 times H. H means the height. Height is 1 meter. 1 meter times this is the effective stress. Because water is not there, then we don't have to subtract the pore water pressure. NQ, that is 7.44. Second part is also done. Then 0.4 times 0.4 times gamma. Gamma is 17.8 times B. B is the width of the foundation, that is 1.5 times N gamma. N gamma is 3.64. So this is how you can find the ultimate bearing capacity. Units will be kilonewtons per meter square or kilopascals. Please tell me the value and please ask any questions regarding this one. If you don't have any questions, please tell me the answer.
So 520.862.
520 means 520.
Yeah, 520.862.
862. Right. Any questions? Right. What does the question ask us is determine the allowable gross load on the foundation with the factor of safety 4. Factor of safety is given, allowable gross load දෙක ගන්න. Then factor of safety equals Q ultimate divided by Q allowable. Q means a stress, right? This Q is a stress, but what do they ask is a load. Allowable load දෙක ගන්න. First we will find the allowable stress. Therefore, allowable stress is equal to QU divided by factor of safety. හරි නේද? Q allowable equals QU divided by factor of safety. මේක මෙහෙට ගියා මේක මෙහෙට ගියා. That means 520.8 divided by 4. This will be in kilonewtons per meter square. This will be in kilonewtons per meter square. But what we need is allowable load. To find the allowable load, the allowable stress have to be multiplied by the area. Right? Therefore, this value should be multiplied by 1.5 times 1.5. Then you will get the answer in kilonewtons. Clear? Right. Please note it down, and if you have any questions, please ask. Otherwise, give me the answer. Yes, if you have any questions, please ask. Any questions? Now I may draw some figure to understand. I mean, what is this question?
The answer is 292.98.
292.98. Okay, I don't know the answer. This is 130.2. No, 1.1. Yes. Any more questions? Any questions on this? If you don't have any questions, then we will move to the Mayhoff's method. Do the same thing using Mayhoff method, right? Do the same same question using Mayhoff method. Now I will explain what this is. QU equals, this is the equation. C dash is the cohesion. NC, now for the 12.9, equation 12.9, you have to use 12.6. What is this? Yes, for this Mayhoff's equation, NC, NQ, and gamma values, then you will have to use this table. Sorry, I was just telling. Later, I found that I was not connected. This Google thing is not that much convenient, appa. So I wrote this everything, and later I found that this stop sharing symbol is not there. Then this FCS, you can find this using this equation BOL blah blah like this, and please tell me the values. And since I was telling this one, because this DF over B is less than 1, DF is 1 and B is 1.5. Therefore, you should use this condition A, not this condition B. Right? Please tell me these values. Yes, please give me the answers quickly, because we have to continue for the next method also.
So 1.421.
Yes, thank you. FCS the
FCS.
1.421.
1.
Okay, thank you. What about the other values? Oh, මුලදී හිටියා නේද මේ මොනවාද? පළවෙනි දවසේ හිටියා නේ එන සෙට් එකක් වැඩකාරයෝ. කෙනෙක් කිව්වා මේ මොකද්ද PhD කරන්න ඕනේ අනම්මනම් කතන්දර ටොක්ස් ටිකක් දුන්නා අද නෑ. කවුද මතකත් නෑ. මට මතක නෑ කවුද කියලා.
So 1.364.
Right, thank you very much. What is your name? නම දැනගන්න කවුද මේ? මම මොකද Google දැන් Zoom වල නම් කතා කරන කෙනාව පේනවා. මේන් කතා කරන කෙනාව පේන්නේ නෑනේ. අනේ කවුද නම?
Lahiru sir.
Lahiru Tushar. All right, okay. Thank you, Lahiru. This is 0.6 නේද? මේ 1.5 1.5 කැපිලා ගිහලා 1 minus එහෙම කතා
Yes,
කරනකොට තමයි එතු ඔයාලට ඔයාලට වරදින දේවල් හිතා ගන්න පුළුවන් ඊට පස්සේ ඒකට ඔයගොල්ලෝ වැඩ කරනවා එතකොට ආයෙ බලන්න ඕනේ. Right, FCD, FQD, F gamma D is 1. These two.
One 1.267.
Thank you. දැන් එහෙම workout කළාම ඔයාලට ආයි ඔය question එකක් exam එකේදී ආවත් ආයි පටස් කරලා හදන්න පුළුවන්. මොකද වැඩේ දන්නවනේ. මේක මම calculator ගහනකොට පොඩ්ඩක් පරිස්සමෙන්. If you sometimes this might there, I mean you will need the bracket here when you type that in the calculator.
So 1.315.
Okay, thank you. And we have some more. That is this one. Yes, that should be, I think it should be something like this name. 1 minus beta is now inclination of the load on the foundation with respect to vertical. Beta should be 0. Then 0 divided by 90. That means there is 1. 0 divided by 90 is 0. And this is also 1. Then F gamma D is 1. Right. Now this takes some time. I mean, using the Mayhoff method because we have so many parameters to find. Right. However, we have found everyone. Then apply those values. I mean, substitute those values and find QU, and you can follow the same steps. QU and the allowable stress and the allowable load. Just tell me the answer quickly. Quickly. Please substitute these values and tell me the answer. C dash is 1.15.2. NC, we will have to check that this table. NC 14.83. FCS 1.421. FCD 1.267. FCI 1 plus Q. Q is the effective stress at the bottom of the foundation. Q, that is 17.8 times 1. 17.8. NQ. NQ means 6.4. FQS 1.364. FQS में FQD 1.315. FQI किधर पे? हमें FQI is 1. Even though there are so many factors, most of the factors are 1. Then half 0.5 times gamma 17.8. D 1.5. N gamma 5.39. Gamma S 0.6. F gamma D 1. Right. You can find this answer in kilonewtons per meter squared or kilopascal. Then you will get slightly different answer. But please tell me the answer.
So, so this FCS value is strong. I actually got the result from the other table.
Right.
It
Then
should be
this one has to be corrected.
1.431.
Right. Good. 1.431.
1.
Okay. Then වැරදිච්ච එක හොඳයි. It is better if then after, during the exam you will not get get it wrong. Eh? Right. Good. 1.431. Then this should be 1.431. Yes.
431.
Then this should be 1.431. Thank you. You quickly do it.
The QU equal 653.948.
Yes. Yes.
QU equal the QU equal
Sorry.
653.948. 53.
600.
53. 53.948.
I need 653 point.
163.48.
Please check the others also.
367.85.
Right, and thank you very much. Now, from the we do it as 292 and this one 367. Somewhere around 300 to yeah, the value might be somewhere around 300 to 360. Right? The two method gives us two values. That is okay, and that is how we can find the ultimate bearing capacity or the ultimate load or the allowable load. Uh, I don't know why it is disconnecting. Not a network problem. The network is there. You lost your network connection. Try to reconnect. Okay, sometimes it may be due to the rain. Oh, okay. Let's move ahead. However, in the next week, we will be doing some real-time example to find the width of the foundation for our requirement. Now we will see what happens when there is water table. Right? Right. Right. Now we will see how we can modify these equations for the bearing capacity equations when there is a water table. Equations 12.3, 12.5, these were developed determining the ultimate bearing capacity based on the assumption that water table is located well below the foundation. Right? The example that you did now was, in that example, it was assumed that the water table lies well below the foundation. Now we will see what happens if the water table is close to the foundation. If the water table is close to the foundation, some modifications of the bearing capacity equation are necessary, depending on the location of the water table. Here we have three cases. Case 1, water table is in between the ground surface and the foundation bottom. The water table is, the groundwater table is in between the ground surface and the foundation depth. The case 2 is the water table, groundwater table is at a depth of D, which D is greater than less than B. From here up to a depth of B. Right. Case 1, if the water table is located so that D1 means the depth to the water table. This is D1, right? This is D1. The depth to the water table is in between 0 and foundation depth. Zero and foundation depth, in between these two. The factor Q in the bearing capacity equation takes the form Q is the effective stress or effective surcharge. That is same as this one, effective stress. This is the effective stress equation. That means if you add these two, if you add this part and this part, addition of these two will give us the total stress, and this times this, that will be the effective stress, right? Therefore that becomes same as what we have discussed. Q will be effective stress, and how to find that Q is total stress minus pore water pressure. Right? This will be the addition of these two parts will be the what is it, these two parts, addition of these two parts will be total stress, and this would be the pore water pressure. And gamma set, yes, is saturated unit weight, blah blah blah. There unit weight, two unit weights are given, saturated weight and the other one. Also, the value in gamma in the last term of the equation has to be replaced by gamma dash. The last term has to be replaced by gamma dash. The last term of the equation, that is this one. This one. This gamma has to be replaced by gamma dash, where gamma is gamma set minus gamma w. Right? That happens when the water table is in between these two. And the case 2 for a water table is located so that D is in between 0 and B. There Q equals gamma dF. That is also the stress, no problem. But the important thing is this equation gamma dash, the factor gamma in the last term should be replaced by this factor, this gamma dash. Right? These are the modifications when you have a water table. Right? If you have anything to note down, please note it down. There are 3 cases: case 1, case 2, case 3. Case 3 is what we have discussed. The water will have no effect on the ultimate bearing capacity. If you have anything to note down, please note it down. And then if you have to note down anything, you can note down from here this one. right? And these are the equations for the factor of safety. Actually, we have used these things already. Allowable stress is equal to the ultimate stress divided by the factor of safety. Or else you can take this factor of safety here. Factor of safety equals ultimate divided by allowable. And that is the net stress increase. Net stress increase equal to the ultimate bearing capacity divided by the factor of safety. Or the ultimate net one can be the net ultimate bearing capacity is defined like this. Yes, these are the equations that we have already discussed, and this is the example that we discussed. And there are answers here. Right. In the next example, we have the water table here. Right. Shall we quickly do this one? The square footing is shown here. Determine the safe closed load. Factor of safety is 3. Gamma, C dash, all the values are given, right? Right. Quickly do it. And this gives the answer in Mayhoff's method. Shall we try it in because the answer for the answer in the Mayhoff method is given. Therefore, shall we try the Tersagh's method using Tersaghi method, right? Yes, try with the Tersaghi's method. Yes, any more questions?
Sir, this 12.4 figure,
Yes, question.
it's not clear, sir. This figure
Yes,
12.4.
කැඩි කැඩි එහෙම.
Sir, figure 12.4 එක පොඩ්ඩක් පැහැදිලි මදි. water table එක තියෙන එක.
Sorry Lahiru, ඉස්සෙල්ලා කැඩි කැඩි ඇහුනේ. I heard some
Sir, that
disturbance.
figure 12.4, it's not
Okay.
clear.
12.4. What is that? Right.
That,
This one.
yes, sir.
This is case 1. This is D1. Let me check with the book. First, I will explain. What says here is case 1. This is D1, D2. This is ground order table. This is DF and simple D. This is also ground order table for case number 2. Let me see some the book. We have the book with us. The Fundamentals of Geotechnical Engineering. No, that is not the book. I have the hard copy with me, but yes, that is given for the exam so that you can. I think this is clear, ne?
Yes, sir. Yes.
Yeah. This is the case. This is the thing. For the exam, in the previous here this was given. Otherwise, keeping this in mind is somewhat difficult. No, they were given. Yes, any more questions? Actually, see the answer in what is it? Mayhoff's method. They have taken this equation, and Q is found as, now they have first what they have found is C dash is 0. Since this is C is 0, one part can be removed. Therefore, you will get only two parts. The cohesion is 0. Therefore, you will get only two parts of the equation. And they have found NQ and N gamma. NC is not needed. NQ and N gamma. Then for the Mayhoff's equation, they have found FQS, FQD, F gamma S, blah blah blah, all those factors. And then effective stress, total stress minus water pressure. You can take the same value. And then they have applied the equation, and ultimate one was 700. And from this Terzaghis method, you will get a rough approximate value to this one, and factor of safety is 3, and you can find this one. Right, that is how you can find the ultimate bearing capacity of a foundation. Right, shall we just quickly go through what we have done today? Shallow foundations. This is the book, and we discussed so many concepts. Ultimate bearing capacity, and this is the equation that we use. That is the Terzaghis equation, and this is for the square footing, and this is for the circular footing. And first we have to find NC, NQ, and gamma values, and then or else you can use these equations also. For the exam, you will be given these equations, right? Wait, for the exam, you will be given these equations to calculate this what is it? the bearing capacity. And then Meyerhoff's equation. From the Meyerhoff's equation, for the Meyerhoff's equation, there's a different table for NC, NQ, and gamma, and you can find these factors. There are so many factors in the Meyerhoff's equation, and the modifications for the bearing capacity equation for the water table. When the water table is available, there are some modifications that you have to do. Right. In the next week, we will be doing these calculations for inclined forces and eccentrically loaded foundations. We will just go through them in the next week with the real time example. And we will meet in the next week. Please come and attend and work out those questions during the class itself. Then it will be easy for you to study for the exam, right? Okay, then I will conclude here, and we will meet in the next week.